In this lecture, we're going to be talking about alpha halogenation. We're going to look at the HVZ reaction. We're going to look at also alpha halogenation under acidic and basic conditions and the differences we'll get there. Let's get right into it here. So, for acid catalyzed alpha halogenation, we're going to notice that we're going to get maybe a monosubstituted brominated ketone containing product. Now, what we'll notice with base catalyzed is we're going to get a carboxylic acid. Now, I know it's very overwhelming here that I'm putting these on the board, but we're going to go through each respectively. I just want you to realize the difference. If I use an acid, we're going to get the brominated ketone, the alpha brominated ketone. If we use base catalyzed, we're going to do what's called the haloform reaction. We'll talk about that, but not right now. It's going to make a carboxylic acid. So we prefer to go through the enolate form because it's just easier and faster. But in this case with bromination, it turns out when you use this, you're going to get a carboxylic acid. Now, before we get into actually what the haloform is, let's do it under acid catalyzed. Now, we're going to see some similarities, but some differences. Now, with our ketone, we're going to notice, okay, first step is make the enol, make that reactive species. So H3O comes in, the ketone's like, hello, I'll steal your hydrogen, make you just water. And the protonated carbonyl is like, oh, I just realized I messed up. I have a hydrogen on me. I don't want that. So water's going to come in, and he says, okay, I will, instead of directly getting rid of this, I'll turn you from a ketone into an alcohol. Sad life for our poor carbonyl here, but that's just how the cookie crumbles sometimes. So we form the enol, right? This is the first step. Next, we're going to have the bromination step. The alcohol is like, I don't want to be an alcohol. I want to become a ketone. I'm going to do tautomerization. Now, it might attack a hydrogen source, but in this case, let's say it attacks instead the bromine. This is the key part of the mechanism. Let's say it attacks a bromine, okay? So it's going to kick out those pi electrons, and we'll lose a bromine a bromine anion. We're going to get bromine attached, and we're going to get this intermediate. Now, notice we just have the protonated carbonyl again like we had here, so water now comes in. He's a little late to the party, but you know. He'll pick up a hydrogen, dump it onto the carbonyl, and we'll have our product. Now, depending on which alkyl halide you have, this might happen twice, 3 times, but it usually won't go that far. Alrighty? So I want you now to realize there's a difference that happens with basic conditions. Now, notice here we had to protonate the carbonyl and do all this stuff to get here, but under basic conditions, it's a lot simpler, right? So I just showed you this reaction. This is called alpha halogenation under acidic conditions. Now let's change the acid into a base. And we know that that now forms a carboxylic acid. Why is this? Well, you have to actually look at the mechanism. You have your ketone, and instead of going through all that junk that might hinder our polyalpha bromination, now let's use instead just one simple step where we say, okay, I'm going to attack this hydrogen here, kick up electrons, all right? Form the enolate. But what happens here is, okay, it's going to immediately go. It's going to see the bromine. We have one less step here. Attack the bromine and reform carbonyl. This is going to add, because the steps are shorter, because we're under basic conditions, and because this bromine makes this proton more acidic, it's going to happen again and again and again and again. Okay, and it's going to happen 3 times specifically till we get what's called a CBr3 leaving group. Now, because of induction, because this carbon will have a negative charge in the induction of the bromines, it makes this stabilized and therefore this a good leaving group. Alrighty, so what happens is it's going to say, okay, sodium hydroxide, form a hydrate. Remember from what I said in the first lecture, that OH is still making hydrates, but there's something different that will happen. The sodium hydroxide is going to come in, it's going to say, okay, hello, I'm on you now. And then we have the O and the OH. Now, normally what would happen is, well, we're making hydrates, it's just going to kick the OH right out, right? It usually does that because it can't just kick out a carbon or a hydrogen very easily. But here, notice, what's the better leaving group? An OH or the CBr complex that we talked about that has that induction stabilization of the carbon anion. Well, it's going to be that group there, and what happens is it's not going to kick out the OH like it normally would under all the other conditions we've seen. It's going to kick out this group here, and we're going to lose that CBr3 anion. Okay, and that's going to form with the sodium, and this is actually going to be a quite stable process. So what we actually get is a carboxylic acid. This is very important to see. I'm going to go through this one more time before we move on to the HVZ, and then we'll do a couple example problems. But notice, we're gonna use a ketone, and we're going to get a carboxylic acid. This is because, and the ketone must be on the end here, it must be a primary carbon, or else you'll just get polybromination and you won't get anything else. But notice, it's going to go once and then 3 more times through this process by forming the enol, attacking a bromine gas molecule, and doing that a couple more times to form that tribromide complex on the carbon. And then NaOH is going to say, okay, I'm going to try and form a hydrate. It tries it, but it fails, and it just makes a carboxylic acid. So the last reaction of this section of this chapter is called HVZ, which is called the Hell-Volhard-Zelinsky reaction. Now, it follows through this process where we take a carboxylic acid and we do alpha bromination to it. Now, remember in the last little section we had here, we talked about the haloform. We made carboxylic acid. So maybe in a synthesis problem, you'd say, okay, I'm going to make a carboxylic acid by the haloform, and then I'm going to do alpha bromination of that by using iron tribromide, bromine gas, and sodium hydroxide. What happens here? It's quite simple. We're going to take, remember in the carboxylic acid chemistry chapter you learned what iron tribromide does with bromine gas. It's going to make, and you need pyridine too. It's going to form our acyl bromide, all right? What happens next is we're going to then form an enolate. So this will have a negative charge, and we'll have an enol here. Then we attach that bromine group on. All right? So we're going to kick down electrons, and then in the presence of aqueous sodium hydroxide, now you need to add water in a separate step, so you add your reagents here. Then in an aqueous environment, you add water. And remember what happens with acyl bromides, acyl chlorides, and water? They hydrolyze back into carboxylic acids. That's exactly what's going to happen here. So we're going to get that. And notice we have an alpha substituted carboxylic acid. So that's exactly what happens here. We have our carboxylic acid. We brominate it through the iron tribromide. We're going to form an enolate, put a bromine there, and then we're going to get our alpha substituted or alpha halogenated carboxylic acid. That's the HVZ. You don't need to know the mechanism every single little step, although I'm sure it wouldn't be hard for you to figure that out. It just goes through this process. And that's why we observe what we observe when we do the HVZ reaction. So let's go through 3 practice problems. Now for this first one, we're asked to devise a synthesis. How can we go from this to this? You will need to have an understanding of, carboxylic acid chemistry and alcohol chemistry to solve this one. Okay, so let's think about how we can put a carboxylic acid here, because it seems like this was converted to first a carboxylic acid. So I know that if I use, what would I want to use here? I don't want to make an aldehyde, I want to make a ketone. So I'm going to use this chromate salt, NaCr2O7, and I'm going to use H2SO4 to in situ create chromic acid, which will then form or react with our primary alcohol to make this carboxylic acid. I know that from this chapter we have HVZ, Haloform-Zielinski reaction, if I use iron tribromide, bromine gas, a base, and then in a separate reaction I have water. I know that that will alpha halogenate our carboxylic acid. So notice this is a two-step synthesis. First we make the carboxylic acid, then we use HVZ to get the product of interest. Let's move on to another practice problem. So in this problem we are asked, given this aldehyde and we react it with first acidic conditions and bromine gas, aqueous acidic conditions, and then we use pyridine base. In a second separate step, what is not only the product, but what is the mechanism? So I'm going to actually work in reverse here. I'm going to draw the mechanism, then the product. So see if you can solve this one here. So under acidic conditions, we first have to make it enol. So we're going to use an acid here. So H3O plus works just fine. We're going to first protonate our carbonyl. Okie dokie, so we get our protonated carbonyl. What happens next is we're going to get elimination from H2O, from that single hydrogen right there. We're not going to take that one because that's going to put electrons on this carbon instead, which is not an alpha carbon. This is the C double bond O carbon. You wouldn't want to do that. So we'll attack the carbonyl, make an enol, and our next step is going to be, okay, where's our bromine? Hi bromine, how's it going? Time for you to get attacked. All right, we're going to attack the bromine. We're going to put a positive charge on the oxygen. And now we have a bromine here, okay? What happens next is we're going to take pyridine, okay? Because this is under acidic conditions, this will stay like this possibly, or water could come back in. But notice we used acid here. We regained our acid, so we don't really have a basic species in solution, so that's where pyridine comes in. Although I'm sure a stray water molecule could come in and do that, but you know, you drive it better with when you use pyridine. So what we get as our final product is a tertiary alpha brominated ketone product. So that's going to be the answer. This is the product. This is the mechanism. All right, let's move on to one last problem. So in this problem, we are asked, how do we turn this cyclohexanol into that alpha beta unsaturated ketone? How can we do that? Well, let's think a little bit retrosynthetically with what we might know. So I'll draw it here. Here's our product. How can we go from this to something? Well, I remember that from even organic chemistry 1, if we use a base like pyridine here, and we have a bromine sticking out, well, this bromine will just disappear if we heat the solution and use a polar aprotic solvent. It's going to eliminate this way. So if I use pyridine and heat, I'll get this, retro. retrosynthetically speaking. All right, let's continue here. How can we do this? Well, if I have a ketone, well, I know I can use what we just learned, alpha bromination. If I use bromine gas and acid, well, I'll get that product. But notice that's not what our starting material is. Our starting material is an alcohol, and for this we have to use a weak oxidizing agent. You can use any of the ones you've learned. I'm going to use bleach, a weak acid, so I'll use acetic acid, and then we'll do 0 degrees Celsius on that reaction. So now the forwards reaction, so we spoke about this in retro. The forward synthesis would be, okay, oxidize your alcohol using any oxidizing agent. I'm going to use the most green one because green chemistry is important. We're going to make a ketone. Then we're going to do alpha bromination using acid and bromine. And then I'm going to go one step further, use pyridine, and I'm going to heat that solution, put it in a polar aprotic solvent, a polar protic solvent, and what's going to happen is we're going to get our product here, our alpha beta unsaturated ketone. So that was everything you need to know about bromination in the alpha position. You could also do this similarly with chlorines, but I, in this lecture, decided to use bromines. You just use chlorine reagents, especially when you use iron tribromide, you use aluminum trichloride. So in the next lecture, we are going to look at, aldol reactions. Aldol reactions are going to be ketones coming together to form these long kind of chains, which we'll see and talk about in great depth. Have a wonderful day.